This network represents the connectivity of modern finance. Technology is now the literal mechanism through which institutions prove reliability, detect abuse, and maintain systemic stability. Customers demand instant settlement. Regulators require exact traceability. Criminal networks exploit gaps in digital onboarding and cross-border channels with increasing sophistication. To survive these pressures, institutions must ingest, validate, and analyze massive volumes of transactional and behavioral data at sub-second speeds. Faced with this complexity, executive boards frequently default to purchasing artificial intelligence software, treating it as an immediate, standalone solution to operational drag. Bolting an advanced machine learning model onto a disorganized data environment multiplies hidden risk. A predictive model fed delayed or inconsistent data will confidently execute flawed logic at scale, expanding an institution's exposure to failure. Taking a broken manual process and applying a digital interface to it digitizes inefficiency. Institutional redesign requires altering how work is initiated, monitored, and escalated across the entire operating chain. The target state is the AI-native financial institution. Achieving this requires a rigorous, ground-up redesign of core operating systems, data architecture, and human decision pathways. To understand why AI applications succeed or fail in the real world, we have to examine this architecture layer by layer, starting at the bedrock. Advanced AI is an emergent capability of a perfectly engineered data environment. It cannot exist without it. This diagram illustrates a typical legacy banking stack, a tangled web of point-to-point connections linking isolated databases. Over decades, institutions responded to regulations by writing bespoke code, wrapping the core in temporary workarounds that solidified into permanent fixtures. The deciding mechanical limitation of this architecture is its reliance on end-of-day batch processing. Information moves in scheduled bulk uploads rather than continuous real-time streams. If you deploy a live AI fraud detection model on this architecture, it must make instantaneous decisions using outdated context. In an instant payment environment, receiving context 15 minutes late renders detection useless. The hostile transfer settles before the system recognizes the threat. The latency problem is compounded by fragmented identity records. The credit department, the retail channel, and the compliance team often store differing profiles for the exact same customer. When systems log geographic markers differently, the AI model loses its ability to link devices and historical behavior. The algorithm is blinded by inconsistent data. Deploying advanced machine learning on top of a legacy core does not modernize the institution. It automates existing operational fragility. This diagram shows the structural alternative, event-driven architecture. Instead of scattered databases, a centralized middleware hub handles communication using controlled APIs. An API, or Application Programming Interface, is a set of rules that allows distinct software components to exchange data securely and predictably. Under this model, every customer transaction generates a data-rich event, broadcast instantly to every connected analytical module. The architecture simultaneously routes this single event to fraud, anti-money laundering, and treasury models, giving every control function immediate visibility. This alignment is enforced through master data management. It is the strict governance practice of creating a single, reliable source of truth for critical business entities, ensuring all analytical models interpret the event using the exact same definitions. Once data flows are synchronized, institutions must satisfy a rigorous supervisory requirement, proving the origin of automated decisions. This is data lineage, an auditable trail proving exactly how a risk indicator was produced, detailing every transformation rule applied to source data. Prudential supervisors and central banks demand this traceability, because a major decision on capital allocation or systemic liquidity cannot rest on data that has passed through undocumented technical layers. The predictive quality of any AI model is strictly and mathematically constrained by the accuracy of the institution's memory and data architecture. With clean, event-driven data secured, the institution can activate the AI inference layer. The operational purpose of this layer is to generate early warning indicators. This graph compares two distinct approaches to risk monitoring. The flat line dropping abruptly represents a lagging indicator. It confirms a loss after the damage is done. The cascading wave patterns that align before the drop represent leading indicators, signaling the probability of an adverse event. Predictive analytics moves an institution away from static, rules-based thresholds and allows it to assess dynamic pattern progression as it forms. We see this clearly in fraud prevention. Instead of waiting for a reported theft, the AI model synthesizes login cadence, device familiarity, and transaction velocity. If the session deviates from the behavioral baseline, the system blocks the hostile transfer. A similar logic applies to treasury operations and intraday liquidity management. By analyzing real-time payment queue buildup and mailing deposit behavior, the AI flags incoming liquidity pressure hours before a formal shortfall registers on the balance sheet. Predictive analytics does not predict the future. It identifies the mathematical structure of a risk event while there is still time for management to act. An advanced predictive model cannot operate autonomously. It must be encased in a strict governance framework. This chart demonstrates a phenomenon known as model drift. Model drift occurs when an algorithm loses predictive accuracy because the live, real-world data it processes has deviated from the historical data used to train it. Drift is triggered by external reality. Criminal networks adapt tactics to bypass thresholds, and macroeconomic shifts alter how customers utilize deposits. Because behavior changes, static assumptions are dangerous. This mandates continuous backtesting and human-in-the-loop recalibration to ensure the model remains aligned with current market conditions. This human oversight leads directly to the non-negotiable requirement of explainability. Denying a line of credit, filing a suspicious activity report, or executing a central reserve operation cannot rely on opaque black box logic. Investigators and supervisors must know exactly which signals drove the warning. In a highly regulated environment, the purpose of AI is high-speed signal processing and decision support. It is not autonomous policy execution. Advanced AI sharpens attention and reduces investigative noise, but human accountability remains the final, critical component of the control environment. Success in the next era of finance belongs to those who integrate clean data, resilient architecture, and human judgment into a single, disciplined control environment.